Imagine someone offering you $1 million, not for climbing Mount Everest, not for inventing a revolutionary technology, not for discovering a new planet, but simply for proving a mathematical statement, a statement written more than 160 years ago. Thousands of brilliant mathematicians have devoted their lives to solving it. Entire careers have been built around this single question, yet today, it remains unsolved. This is the Riemann hypothesis, and before this video ends, you'll understand why many people consider it the most important unsolved problem in mathematics. At first glance, this seems ridiculous. How could a problem about numbers possibly matter? The truth is, prime numbers quietly power much of our modern world. They're woven into the mathematics behind digital security, internet communication, banking, and countless algorithms that run every day. If mathematics has a periodic table, prime numbers are its atoms. Everything else is built from them. Understanding how prime numbers behave isn't just a mathematical curiosity. It's one of the deepest questions humanity has ever asked. Let's begin with something surprisingly simple. A prime number is a whole number greater than one that can only be divided evenly by 1 and itself. 2, 3, 5, 7, 11. They may seem ordinary, but they're unlike any other numbers. Take 12. It can be broken apart into 2 times 6, or 3 times 4. Prime numbers refuse to break. They are the indivisible pieces from which every whole number is constructed. In mathematics, nothing is more fundamental. Here's the astonishing fact. Every whole number greater than 1 can be built from prime numbers, and in only one unique way. Just as every molecule is made from atoms, every integer is made from primes. This idea is known as the fundamental theorem of arithmetic. It tells us that prime numbers are the foundation beneath all of mathematics. But something strange happens when mathematicians try to predict where the next prime number will appear. There seems to be no obvious pattern, only mystery. And that mystery is exactly where our story begins. If prime numbers are the building blocks of mathematics, then surely there must be a way to predict where they appear. But the more mathematicians searched, the stranger the pattern became. Sometimes 2 prime numbers stand right next to each other. Sometimes hundreds of numbers pass without finding a single one. The primes looked random, yet they couldn't possibly be random. Something was hiding beneath the chaos. For over 2,000 years, some of the greatest mathematical minds searched for a pattern. They discovered beautiful formulas, remarkable theorems, powerful techniques, but none of them revealed the secret rhythm of the prime numbers. Every new discovery solved one mystery, only to uncover an even deeper one. By the middle of the 19th century, many believed the problem might simply be impossible. Then, a quiet German mathematician changed everything. Bernhard Riemann wasn't trying to list prime numbers one by one. Instead, he asked a completely different question. What if the secret of the primes wasn't hidden on the number line at all? What if it existed somewhere else, in a completely different mathematical world? In 1859, Riemann published an 8-page paper. Those 8 pages would become one of the most influential documents in the history of mathematics. Until now, every number we've discussed has lived on a straight line, but Riemann stepped into an entirely new universe, a universe where numbers have 2 parts, a real part, and an imaginary part. Together, they form what mathematicians call the complex plane. At first, this may sound like an abstract invention, but complex numbers are everywhere. They describe electricity, quantum mechanics, signal processing, and as Riemann discovered, they also reveal extraordinary patterns hidden inside the prime numbers. To explore this new world, Riemann used a remarkable equation. Today we call it the Riemann zeta function. At first glance, it looks like just another infinite series, but hidden inside this single equation is a map of the prime numbers themselves. And the deeper mathematicians explored this map, the stranger it became. What happens when the value of the zeta function becomes exactly 0? These special locations are called zeros. At first, finding them seemed like nothing more than an interesting mathematical exercise, but as more and more zeros were discovered, A remarkable pattern began to emerge. They weren't scattered randomly across the complex plane. Instead, they appeared to line up in an astonishingly organized way. Riemann discovered that the most interesting zeros all lived inside a narrow region called the critical strip. Imagine searching for treasure across an entire planet, only to learn that every clue lies within a single narrow valley. Suddenly, the search becomes much more focused. Within this strip, mathematicians found infinitely many of these mysterious zeros, and something about their positions refused to be ignored. Exactly halfway through the critical strip lies a single vertical line. Its real part is one half. As mathematicians calculated more zeros, they noticed something extraordinary. Every non-trivial zero they found landed perfectly on this line. Not close to it, not approximately, exactly on it, again and again and again. That observation inspired one of the boldest mathematical predictions ever made. Riemann believed this wasn't a coincidence. He proposed a breathtakingly simple idea. Every non-trivial zero of the Riemann zeta function lies on the critical line. That's it. The entire hypothesis can be stated in a single sentence. No complicated pages of equations, no endless definitions. Just one elegant claim, and yet no one has ever been able to prove it, nor has anyone found a single exception. Modern computers have searched farther than Riemann could ever have imagined. They've checked billions of non-trivial zeros. Every single one lies exactly where the hypothesis predicts. But mathematics is different from science. No matter how much evidence we collect, evidence is never proof. Somewhere among infinitely many possibilities, one single exception would be enough to destroy the hypothesis forever, and that is why the mystery remains unsolved. At this point, you might be wondering, why does any of this matter? After all, the Riemann hypothesis is just one mathematical statement, but mathematics is like a giant tower. Every theorem rests upon earlier discoveries. Some ideas support only a few bricks, others support entire floors. The Riemann hypothesis is one of those foundations. If it is true, hundreds of important mathematical results become dramatically stronger. If it is false, mathematicians would have to rethink decades of work. Prime numbers appear in places most people never notice. They play an essential role in number theory, computer science, coding theory, and modern cryptography. The Riemann hypothesis wouldn't instantly unlock every encrypted message on Earth, but understanding the true distribution of prime numbers could reshape future mathematical techniques and influence how tomorrow's algorithms are designed. History has shown that today's abstract mathematics often becomes tomorrow's technology. If the statement is so simple, why hasn't anyone proved it? Because mathematics isn't about checking examples. You could verify a billion cases, or even a trillion. That still wouldn't prove something true for infinity. A proof must explain why every possible case works, not just the ones we've already seen. That leap from observation to certainty is one of the greatest challenges in all of mathematics. To recognize problems of extraordinary importance, the Clay Mathematics Institute announced 7 Millennium Prize problems. Each carried a reward of $1 million. One has been solved, 6 remain. Among them, the Riemann hypothesis stands as perhaps the most famous, not because of the prize, but because solving it would illuminate one of mathematics' deepest mysteries. Somewhere in the world, a student may already be thinking about this problem. Perhaps the person who eventually solves it hasn't even started university, or perhaps the answer will require entirely new mathematics that hasn't been invented yet. For now, the Riemann hypothesis remains a reminder that even in an age of artificial intelligence, quantum computers, and space exploration, human curiosity still has frontiers left to conquer. Prime numbers look random, yet beneath their apparent chaos, many mathematicians believe perfect order exists. The Riemann hypothesis is our attempt to describe that hidden order, and for more than 160 years, it has resisted every attempt to prove it. Perhaps one day, someone will finally reveal the pattern. Until then, the mystery continues.